Hello all. I thank God for another opportunity to take you through this lecture. We are going to look at screws, fasteners, and the design of non-permanent joints. And first of all, we will look at screws. So a screw here is mainly a machine element that have various applications in engineering, and some can be used for both nuts, for screws, uh, for fastening components together. We can have its application also in the transfer of power from one point to the other in terms of um, screw jacks, like also the lead screw of a lathe machine. We also have like the screw in the bench vise. All right, so those are various applications of screws. There are some terms in screws that we are going to look at. The first one here is the pitch of the screw. All right, so when you look at this diagram over here, the pitch of the screw is this distance here from that point to that point. So simply, the pitch of the screw is the uh, distance between adjacent thread forms, and is measured parallel to the axis of the screw. So if you look at this one here, we have the pitch to be the distance from that point to that point, right? From the center of one thread to the center of the other, measured parallel to the axis. This is the axis of the screw, so measured parallel to the axis of the screw. Then we have the major diameter, and then the major diameter is the largest diameter of a screw thread. So that is the distance from that point to that point, which is the diameter of the screw thread. Then we also have the minor diameter, which is the um, dr. That is the letter we use to represent or to denote the minor diameter. And that minor diameter, which is also known as the root diameter, is the smallest diameter of the screw thread. So the distance from that point to that point is the minor diameter. Then we also have the pitch diameter. So the pitch diameter is intermediate between the major diameter and then the minor diameter, and it is the theoretical diameter between the major and the minor. So we have the pitch diameter between the major diameter and then the minor diameter. Then we have, so actually we can say that the minor diameter is the distance from the root, that is the diameter of the root, that is the root diameter, okay, from that point to that point. And the major diameter is the diameter at the crest of the thread, so from this point, the crest here, to the crest there. Then we also have the thread angle, which is equal to 2 alpha. Okay, then the chamfer at the end too is there to help in starting the um, thread, right? So there's some small chamfer of 45 degrees at the end of the thread. Then we also have what we call the lead. The lead, which is not shown, is the distance the nut moves parallel to the screw axis when the nut is given 110. So here, if we have the nut on this screw, as we turn the nut in one complete revolution, the distance it will translate, all right, on this thread is what we call the lead of the thread. For a single thread, the lead is same as the pitch. So if you have a single thread, as in this example here, this is a single threaded element, the lead is equal to the pitch of the thread. So when you turn the nut in one complete revolution, or you turn the bolt in one complete revolution, the moving the translation of the bolt or the nut along the thread is going to be equal to the pitch of the thread, which is for one or for single threaded element. Then we may also have multiple threaded products. In this case, if the product is having two or more threads cut outside each other, beside each other, if we have the thread cut beside each other, a standardized products such as screws, bolts, and nuts all have single threads. But there may be some special applications where double threaded screws are needed. And in such cases, if we have double threaded screws, we are going to have the lead to be equal to twice the pitch. All right, so if the thread is double threaded, then the lead will be equal to 2 times the pitch of the thread. If it is triple, that is, we have 3 threads beside each other, triple threaded, that means that the lead is equal to 3 times the pitch, and etc. So it continues like that. Depending on the number of threads, the lead is equal to the pitch times the number of threads. All right. Then we are going to look at the profile for threads. So mainly in ISO application, we have the metric thread. All right, so metric thread, we have the M and then the MJ profiles. So M and MJ profiles. So let's look at this one. This diagram here is showing us the form of a thread. And this profile here, we can have it for internal if we are looking at it and saying that this is the crest. All right, if we are looking at it and saying that this is the crest, and then this is the root of it, and this is where the thread material is. This can be it can be an internal thread. So this internal thread could be it could be internal or external depending on the way that we are looking at it. But in this case, we have a cross section of the thread. So over here, there are some specifications for the thread. All right. First, we have H. H is the total height of the thread, or the depth of the thread. So this thread is having some angle between the faces of the thread. So from this face to that face, the angle there is 60 degrees. So when we extend this line where they meet to that point there, the distance from that point to this point, the vertical distance is the H, and the H is equal to square root of 3 divided by 2 times the pitch of the thread. Okay, then in that case there are other specifications for the thread which are dependent on the H. Okay, and these are the information we have here. If you want the major diameter for the thread is equal to this distance here. All right, that is the distance, the major diameter, to the other side if we complete it. Okay, then the root diameter or the minor diameter is that one, right, from this side to the other side. Then we also have the pitch diameter. So the pitch diameter is dp, intermediate between the two, and then the pitch. So we have the pitch p, so pitch p, so all the p we see there is the pitch. So if we want, in this case, the distance from this point to that point is p on 4, which is the pitch divided by 4 to give us this flat bottom here. Okay, so if this is an external thread, then we can say that this point here is the crest for the thread, and this is the crest for the thread. Then if it is an external thread, we can say that this is the root. Okay, this is the root. Then for internal thread, this one here will be the crest, and that will be the root for internal thread. So we have the metric, and the metric we have two profiles there, the M and then the MJ profiles. All right, and usually we specify the thread details by using something like M12 by 1.52. So the M shows that it's a metric thread, and then we have the 12, which indicates that the diameter of the thread, which is in this case the major diameter of the thread, is 12 millimeters. And then by 1.75, this 1.75 indicates the pitch for the thread. So in this particular case, we have a thread of diameter 12 millimeters, that's major diameter 12 millimeters, and the pitch is 1.75, and this is a metric thread. The M shows that it is a metric thread, and the dimensions are given in millimeters. Then we also have the Acme square thread and then the Acme thread. Okay, so this thread here, the square and then the Acme thread, are usually used for power transmission. Okay, for power transmission. But before this one, let's go back here and let me explain something. The M and then the MJ is usually not having a rounded root, but for the M is not having a rounded root, but the MJ is having a rounded root. And that is, for instance, in this case, with an external thread, this root here is rounded. All right, and that is usually used in cases where there will be a lot of fatigue, or where we want the boat to have a high fatigue strength factor. In that case, we could introduce the fillet at the root of the thread to act as a stress relief. Okay, so that will help the threaded component to be stronger, and where there will be fatigue forces, fatigue stresses available or present, that will prevent the threaded member from failing due to fatigue. Okay, so let's come back to the square thread and the Acme threads. So these are mainly used for power transmission. So power transmission, like the lead screw of the lathe, like the screw jacks, which are used for lifting objects, and then something like the bench vise that we have in the machine shop that is used to clamp objects tightly together. They use the square thread or the Acme thread. Okay, now we're going to look at one application of these threads or screws. Okay, so these screws are mainly applied or used for power transmission, in just like the Acme thread or screws or the square one. They are used for power transmission, and screw jacks are used, or power screws are used for power transmission. All right, and it's used in the machinery to change the angular motion into linear motion, or to change the angular motion, rotational motion, into translation. All right, and that is used to transmit power from one point to the other. Familiar application includes the lead screw of a lathe, the bench vices, presses, and jacks. Okay. All right. So let's assume that there is a square threaded power screw with a single thread having a mean diameter dm, a pitch p, a lead angle lambda, and a helix angle xi. A helix angle xi is loaded by the axial compressive force F, and we wish to find an expression for the torque required to raise the load, and another expression for the torque required to lower the load. Okay, so let's look at this description we have here in a diagrammatical form. So over here we have this diagram here showing the screw, and we're having a cross section of the where the screw is. All right, so let's say we have a nut here, or the internal screw member where this thread is inside or within. Okay, and there is a force that is acting on this screw. Okay, so there is that external force. So we have that external force, uh, which is the load on the screw. So in that case, we have something like some weight which this screw is to lift or to raise upwards, and the weight is of that load is, say, F, acting on this screw, and the pitch of the screw, we are taking it to be P, and then we have psi to be the helix angle, all right, which is the angle between the uh, vertical and then the inclination or the inclined surface of the screw. Okay, that is a helix angle. Then we have also the lead angle lambda. So we have the lead angle to be lambda, and that lead angle is the angle between the horizontal and then the inclined surface of the screw. Then if we have that, let's cut this out and spread it. So we try to cut out the thread, one complete thread, all right, around. If we are going one complete revolution, we cut at one point and open everything. And then when we do that, and it's going to be like a wedge or an inclined surface. Because of this angle here, this lead angle, all right, and this is a single thread, so we know that the lead is equal to the pitch of the thread. Okay, so we are going to have it open from one end, inclined like this, and that angle here will be the lead angle, and that is the horizontal. Okay, then the lead will be from that point to that point. And if we want to lift the load F, in effect, it means that we are trying to move the object, all right, like a wedge. We are moving the object along this surface. Okay, but the load is coming in this direction, F lying on it, and the force of F will be on this surface, and that is the direction of the force F. Now with this, if we are turning the screw, we will realize that there will be some friction force on this inclined surface. Okay, and as we are turning it, the force that we are using to turn or to raise, as we are turning it to raise the load, the torque we are turning it to raise the load will be the PR, and that will be the direction of that force. There will be a friction force on the surface. Okay, and that friction force would try to oppose the movement of the thread. Okay, so in that case, the friction force, we can determine it by using this formula here. So we have the expression Fn, where F is the friction coefficient on the surface, and N is the normal reaction. N is the normal reaction. at this point here. Okay, so we have N as the normal reaction, and then F the friction coefficient, and then we have N. So we have the friction force to be friction coefficient times N, which will be acting in the opposite direction. Okay, so as we are raising the load, this friction force will try to oppose the raising of the load, trying to push it down that way. Okay, then we also have the the circumference, or the length of the circumference of the screw, to be pi dm. Okay, so where pi dm is the length or the circumference, the length of the circumference, so or the circumference of um, the screw, that is one screw element. So in that case, or one thread element, so in that case, pi dm gives us the, where dm here is the pitch diameter, dm is the, or the median diameter, or the pitch diameter, or let's say the mean diameter, which is also equivalent to the pitch diameter. So we have the pitch diameter here, the root diameter or the minor diameter here, and then the major diameter outside there. Okay, so if we have this expression, how do we determine, if we have this arrangement here, what would be the torque necessary to be able to uh, raise the load F? What would be the torque necessary to be able to raise the load F? And that torque, of course, will depend on the load PR. Okay, so that is the force needed. The PR here is the force needed to raise the load. Okay, so in that case, we have to resolve the forces. All right, we have to resolve the forces on this diagram here. So we can resolve it into X and Y. In the X direction, we are going to have PR moving in this direction, okay, minus N sine lambda. So the normal reaction here, which is also a force, N sine lambda, where lambda is this angle here. Okay, so N sine that angle will give us the the force N in the X direction, okay, and that is of course going to be to the left side, or to the negative sense. So we're going to have that um, force to be equal to N sine lambda, negative N sine lambda. Then the next one will be the force, the horizontal force generated by this friction force here, and that is equal to Fn cos lambda. So Fn here cos lambda will give you the horizontal component of the force Fn, but the sign is going to be in the negative direction, so we have minus. So when you sum everything up, is equal to 0. Then the forces in the y direction, if we resolve all the forces in the y direction, should also be equal to 0. So first we are having F, which is in the negative sign, and that gives us negative F minus Fn sine lambda. So we have Fn here, sine lambda, plus N cos lambda. So we have N cos lambda to give you the vertical component, and that is positive because it's going upwards. That should be equal to 0. We are not interested in the normal reaction, so what we can simply do here is to make the normal reaction the subject of this equation, and also make the normal reaction the subject of this equation. So we are just eliminating the normal reaction. So when we do that, we can equate um, the two expressions after making the normal reaction the subject. Then we make PR the subject of that equation. That gives us PR to be equal to F sine lambda plus this is the force, and then plus the coefficient of friction cos lambda divided by cos lambda minus F sine lambda. So you can do that elimination, and then you equate the two and obtain this expression here. All right. Then if we're able to obtain this PR, what we are interested in is to determine the torque that is needed to raise the load. All right. So over here, we have been able to determine the PR, the load that will be needed to raise, the force that will be needed to raise the load F. We have determined that to be this expression here. Okay. Then when we have determined this, we need to simplify this equation further. We can do that by simply dividing these two expressions, that is the numerator and the denominator. We can divide both by cos lambda. So for instance, over here, we divide this by cos lambda, all right, cos lambda. And then this one we divide by cos lambda. Then these two we divide by cos lambda, and over here to the same thing, lambda. When we do that, we are going to see that we will have the force PR to be equal to F in bracket. We will have tan lambda, because sine lambda over cos lambda is sine lambda, plus the friction coefficient F divided by 1 minus tan lambda. Okay, 1 minus tan lambda. So we have that, but we can see from this diagram that tan lambda is equal to L divided by dm. Okay, so in place of tan lambda here, we put L over dm. In place of tan lambda, we put L over dm, and that is what gave us um, this expression over here. So wherever we have tan lambda, we put the L over pi dm, and over here to L over pi dm. Okay, now if we simplify this further, we can say that we are going to get over here, if we multiply the numerator by pi dm, we are going to get the numerator to be equal to F in bracket L plus pi, okay, FDM. That's the numerator. Then the denominator, we are going to have, if we multiply the numerator expression by pi dm, we're also going to have pi dm minus FL. Okay, so this will give us the expression here, which is what we have in the bracket. To determine the torque, we are aware that the torque is equal to the force times the distance, perpendicular distance, or in this case the radius, okay, r. But we know that the torque, the r is equal to dm on 2. So we have F times dm on 2. F times dm on 2. Okay, so to determine the torque that is necessary to raise the load, we are just going to multiply this expression we have up here, this expression, by the radius, which is dm on 2, and that will give us this expression down here. All right, so this expression now gives us the torque that is necessary, or that will be needed, to raise the load F, the torque necessary to raise the load F. Okay, now what if we are to determine the torque that is necessary to lower the load, the torque necessary to lower the load? If the load is to be lowered, we have to be able to determine the torque that we need. And we can do that by determining the force, or the amount of force that is needed to provide that torque. Okay, so over here, instead of the force needed to raise the load, which is pointing in this direction, now we need to lower the load. Okay, so we have the force in the opposite direction, so we present that by PL, and this gives us the free body diagram. So we have the forces here. The friction, there will be a friction force that will tend to oppose the lowering of the load, that is Fn. Okay, then the load we are trying to lower is still the same direction. There will be a normal reaction, and the lead angle is given there. Again, we have to resolve the forces in the horizontal and in the vertical direction. So if we resolve all these forces in the horizontal direction, we are going to get this expression here. Then if you resolve it in the vertical direction, we are going to get this here. Okay, then because we are not interested in n, we can eliminate n from these two sets of equation. And when we do that, make PL the subject. All right, so if we do that and we equate the two, and then we make PL the subject, we are going to have this expression here as the force needed to lower the load. Then from here, we can divide this by cos lambda. All right, the numerator and the denominator, we can divide by cos lambda. And when we do that, we are going to have what we have here. Okay, so if you multiply again the numerator by pi dm, you will get this expression, and the denominator by pi dm, you also get this expression here. Okay, then to determine the force, the torque needed to lower the load, TL will be equal to F times the radius. Okay, so we have the dm divided by 2. So in this case, this expression here without the dm on 2 is equal to this force. So this force here times the radius, which is dm on 2, will be equal to the torque needed to lower the load. All right. Okay, so this expression that we are having here is the torque needed to overcome the load, or to lower the load. So partly this force, this torque, is used to overcome part of the friction in order to lower the load. But in some instances, it may turn out that the lead for the screw could be very, very large. Okay, and when the lead is large, or the uh, friction is very low, you may end up having this expression here, this one, this expression here, to be negative. Okay, so because this expression, we have pi fdm minus L. If the lead is so large and it's larger than this expression, you are going to have it to be negative. Or in cases where you have, see, the friction to be very small, the friction coefficient is so small, we may end up having this expression to be negative, which will turn all this to be negative, and in effect to be having a negative torque. So if the torque is negative, what it means is that the load will lower itself. Okay, so in such an instance, you may have the screw turning to lower the load without the application of any external force or effort. And in such cases, we have either the torque to be equal to a negative value or it's zero. When a positive torque is obtained from this expression here, then we can say that the screw is self-locking, right? The screw is self-locking, and in order to attain that condition, it means that this expression pi fdm should be greater than the lead. Okay, then when it's greater than the lead, then we are sure to achieve a self-locking condition. All right, now when we divide the both sides of that equation or that inequality by pi dm, where we have pi fdm to be greater than L. If we divide this by pi dm, if we divide this by pi dm, and then this other side too by pi dm, we'll end up getting f to be equal to L on pi dm. But we know that this L on pi dm here, this L on pi dm is the same as tan. This should be f should be greater than pi dm, L on pi dm. Okay, and this pi dm is the same as tan lambda. All right, from the expression we derived earlier, the same as tan lambda. Okay, so in this case, we can say that the self-locking is attained when the coefficient of friction is greater than the tan of the lead angle. Okay, so self-locking is attained whenever the coefficient of friction is greater than the lead is greater than the tan of the lead angle, okay, of that thread. Then we can say that there is self-locking, the screw is self-locking. Now we can also determine the efficiency of a power screw, right? And in case we let's say f or the friction coefficient to be equal to 0, which means that there's no friction present in the system, we can say that this equation that we have here, which is this equation 2.7, all right, if we have the coefficient of friction to be equal to 0, that means that this is 0 and then this one is 0. We are going to have dm cancelling dm here. Now we have fl on 2 pi. Okay, so we'll end up having this expression here. So assuming there is no friction present or friction force present in the system, we can say that T naught is equal to FL on 2 pi. So this is an ideal condition where we don't have friction in the system, by setting that there's friction in the system. And in that case, we can have this as the torque that is needed to raise the load. Okay, and therefore we can calculate the efficiency of the system as T naught divided by TR. So the TR here is the torque needed to raise the load when there is friction present, and the torque needed to raise the load when there is no friction present is 30 knot. So we have the efficiency to be equal to, when there is no friction, the torque needed to raise the load divided by, when the presence of friction is there, the torque needed to raise the load. All right, so if we put this expression into this equation, we are going to have the efficiency to be equal to FL divided by 2 pi times TR, where TR is the force needed to raise the load when there is friction present in the system. And that TR, we already have the expression for it. We have determined that expression already. Okay. All right. So this equation that we have looked at earlier, we have been able to develop those equations for square threads where the normal thread loads are parallel to the axis of the screw. In case of Acme or other threads, the normal thread load is inclined to the axis because of the thread angle 2 alpha and the lead angle lambda. Since lead angle are small, this inclination can be neglected. Alright, so for Acme threads, the lead angle are small and we could neglect the lambda. Alright, and if we neglect it, then we may consider what we have over here. So in this case, we have Acme thread, and the force, the load that is to be carried or to be lifted, F, is acting in this scene. That is a load. Okay. Then there is the angle 2 alpha, or there's the angle alpha, which is the angle between the scene of action of that load and then the normal to the surface of the thread. So this angle here is the alpha. This angle is the alpha. So the same as this angle. So we have the thread angle, or the thread angle is the thread angle is the 2 alpha. So half of the thread angle, all right, that is the angle between the thread and the horizontal. So this angle here is alpha, and then that alpha is the same as, if you draw a line normal to the inclination of the thread, that line will make an angle of alpha with the vertical axis. Okay, so that is alpha there. All right, then if that is the case, we can say that the force in that line that will be acting this direction will be equal to F cos, it will be equal to F divided by cos alpha. Okay, that will be this force that will be acting this scene. Now that is the force normal to the surface of the thread. Okay. All right. Then if that is the case, we can determine the TR with this expression here. All right. So the effect of this lead angle alpha is to increase the friction force by wedging action of the thread. Therefore, the friction terms in that equation 2.7, which is the equation we have here, this equation, the friction term will have to change. Okay, so it changes to this. So we have the friction term there to be pi FDM sec alpha, and then this one to be pi FL, which is the friction coefficient times the lead times sec alpha. Okay. For power screws, the Acme thread is not as efficient as the square thread. So the square thread is more efficient than the Acme thread when being applied in power screws because of the additional friction due to the wedging action. So this wedging action there, this wedging action on the surface here, which increases the surface area of the screw, ends up making the screw inefficient for power screw applications. Okay. All right, and also it is often preferred because it is easier to machine and permits the use of split nut, which can be adjusted to take up for wear. Okay, so though the square thread is efficient than the Acme thread, the Acme thread is often preferred because of some other advantage, and that is because it permits for split nut, where we can put two nuts or one nut which is split into two. It can allow it, we can use it on the Acme thread, and also it's easier to machine the Acme thread, and that makes it easy. Okay, that makes it easy for it to be machined, and is preferred. And also, especially split nut, if the nut is split, the nut can be adjusted to accommodate for wear. So as you use the screw, wear may take place. But if it is square thread and you are using solid nut, which is not split nut, if the wear takes place, you will end up there will be some loose contact. Okay, but in the case of split nut, if there is wear that takes place, this nut can be adjusted to take up for that wear. Okay. The third component of torque must be applied in power screws application. Usually, the third component of torque has to be applied. And when the screw is loaded axially, a thrust or collar bearing must be employed between the rotating and stationary members in order to carry the axial component of the load. Okay, and we can see that from this diagram here. So in this diagram, we have a collar here. So when this screw is being loaded axially, this collar is there to be able to support. Okay, so there will be a collar bearing that will take up the axial load that is being exerted on the screw. Okay, so in that case, that collar bearing has to be accounted for in the calculation for the screw. If F is a coefficient of collar friction, the torque required is TC, which is the torque required for the collar, is equal to FC DC divided by 2. So the FC is the coefficient of friction for the collar, then the DC is the diameter for the collar, and then divided by 2. So in this case, we have DC on 2 as the say the radius, okay, for the collar. So if you want the torque, F times FC times dc on 2 will give us the torque required to be able to turn the collar. Okay. Nominal body stress in power screw can also be obtained. We may have to determine that. For the maximum normal shear stress, tau is in torsion of the screw body can be expressed as 16T on pi dr cube. That is the maximum shear stress tau in torsion of the screw body. As the screw is being turned, it will be subjected to some twisting. Okay, so it will be in torsion, and to determine that torsional stress in the screw, we need to use this expression over here. Okay, so we have the dr, as we know already, is the root diameter for the screw, which we have looked at when we're looking at the terms in screws. We have looked at the root diameter of the screw. Okay, that is the solid part of the screw. The root diameter of the screw is dr. Then the T is the torque on the screw, which is the torque needed to turn the screw. So either the torque to raise the screw or to lower the screw, that is T. So we have 16T divided by pi dr cube as the shear stress in the screw member. The axial stress sigma in the body of the screw due to load F is given by this. We know that stress is, in short, force over area. Okay, and the force here is F, which is the load that we want to overcome or to lift or lower. Then the A, which is the area, is the cross-section area at the root of the screw. Okay, and we know that A, which is area, is equal to pi d square. All right, pi d square over 4. So when you put that into this place, we are going to have 4f over pi d square. So the d here is the root diameter. All right, so dr square. Okay. So thank you very much. We'll look at some example. Right, so I will upload another video, an example on how to use these many equations that we have looked at. Thank you.